When we say that microservices are independently deployable, we mean that it's possible to upgrade a single microservice without requiring the clients of that microservice to be upgraded at the same time. And this requires great care because it means that you must never make a breaking change to the public interface of a microservice. In fact, it's a good idea to call the public interface a contract, which expresses the idea that it's an agreement between two parties that cannot be unilaterally changed. Now, you might be wondering, how is it even possible to never make a breaking change to your API? Well, the simplest solution is only to make additive changes to your APIs. You could add new endpoints, and you can usually add new properties to data transfer objects, as most serializers can be configured to simply ignore additional fields that they aren't expecting. In some cases, you might find that you need to publish a version 2 of your public API, but if you do so, you still need to keep supporting version 1. Initially, your clients will carry on calling version 1 of your API, but over time they can be updated to call version 2. Unfortunately, it's all too easy for developers to forget about this principle and make a breaking change to both the microservice API, but also update the clients at the same time. When they test this running locally on their development machine, everything works just fine. But now we've got ourselves into a situation where we're forced to upgrade both the microservice and its clients simultaneously. How can we avoid this? One approach that helps is by making individual teams responsible for owning microservices, rather than just allowing all developers to dive into the code for any microservice that they want to change. That way, a client must first ask the owners of the microservice to add a new capability, then wait for it to become available and deployed to production, and only then upgrade their client code to make use of that new feature. Another very helpful practice is to create automated tests around your microservices that explicitly attempt to call using any previous version of the clients that need to be supported. These tests need to be automated as part of a continuous integration build process, and if they fail, you should fail the build, so everyone is aware that there's a problem with backwards compatibility. One pattern to beware of is introducing shared code that both the clients and the microservice itself use. Now, this can be very convenient for a microservice to produce a client package that simplifies the task of calling the service. But if you do take that approach, then you need to take great care to avoid any logic being added into that package that would result in tightly coupling the microservice to its clients and forcing them to be upgraded simultaneously. How can we work out the best way to break our system into microservices? This is a difficult task and easy to get wrong. Drawing service boundaries in the wrong place can result in poor system performance and are hard to change once those services are running in production. So it's worth dedicating some time to considering what your options are in this area. In some ways, your task is easier if you're starting from an existing monolithic application. Very often there will already be some modularization, and some of those modules might be suitable candidates for converting into microservices, especially if they're loosely coupled from the rest of the system through a clear interface. Since microservices own their own data, looking for seams in the database is often a good idea. Are there certain groups of tables that conceptually belong together? If so, identify all the places in the code that read and write from those tables and see whether they can be extracted to form a microservice. A helpful guideline is that microservices should be organized around business capabilities. You may be familiar with the concept of domain-driven design. This encourages us to identify bounded contexts within our applications. This is a way of breaking up the domain model for a large system, with each bounded context having its own ubiquitous language and relating to one specific business capability or subdomain. And often these will map onto the organizational structure of the business. You then define some models that apply within your bounded context. And this means that different microservices will use different models and even might use different terminology for the same thing. We saw that earlier, where the products that eShop on Containers sells are called order items by the ordering microservice and catalog items by the catalog microservice. Although they both relate to a product sold by the shop, they're being used in different contexts, and so they have different properties and they're free to use different names for the same piece of information. Now, it can be daunting to come up with good service boundaries, so a great approach to testing your ideas is to sketch them on a whiteboard and then run through some real-world use cases for your application and see which services would be involved. That can help you identify potential problems if too many services are required to collaborate together to achieve a single business capability. Now, in just a couple of minutes, there's no way I can do justice to the concept of domain-driven design. And if you'd like to learn more about it, then there are several excellent courses available here on Pluralsight that cover it in a lot more detail, including a whole learning path by Vladimir Korikov. There are some pitfalls that you can run into when choosing your microservice boundaries. One is if you simply take all the nouns in your domain and turn them into services. This often ends up with you creating what are sometimes called anemic CRUD services, which are little more than wrappers around tables in a database, with methods to add and update entities, while the logic related to those entities remains distributed across the rest of the system. Another sign that your boundary is not quite right is when you have circular dependencies between your microservices or clusters of microservices which all need to communicate frequently with one another. Let's take a look at the choices made by the architects of the eShop on Containers sample application to see some of these principles in action. There's a catalog microservice responsible for storing details of the products available in the shop. Another microservice tracks what the customers have got in their basket. And then there's an ordering microservice, which is responsible for handling the orders that we've placed in the shop. These three services relate to three distinct parts of the online shopping experience. The catalog microservice supports browsing for products. The basket microservice deals with preparing for a purchase. And the ordering microservice deals with the business process of handling an order. And this separation of responsibilities makes a lot of sense. For one thing, it helps with resilience, as customers will be able to browse for products to buy and put them in their basket, even if the ordering microservice is temporarily unavailable. It also makes sense from a scalability perspective. Each of these microservices is dealing with very different volumes of data and access patterns. For example, the catalogue is potentially very large and needs to support flexible queries as customers are searching for items that they want to buy based on various criteria. That means it makes sense for the catalogue microservice to store its data in a database that supports rich querying, and we can see here that it's using SQL Server, which makes a lot of sense for this kind of use case. Whereas the basket service deals with very short-lived data, so it may not even need to be written to a database. And in fact, eShop on Containers actually uses Redis, a memory cache, to store basket data. The ordering microservice is mostly writing new data to the database whenever a customer places an order. It's got very strict requirements for reliability. We certainly don't want to lose any orders. And it's also handling extremely sensitive data, such as people's addresses and payment information, so its security requirements are very different from those of the catalog service, whose data is freely visible to everyone. There's another microservice here that handles identity, and this helps deal with authentication concerns. And we'll see why that choice has been made later on in this course when we look at security. The marketing microservice relates to a completely different part of the business, to the basket and ordering microservices. This microservice sends out email campaigns, which requires knowing where in the world our potential customers are located. And we can see here that there's a location microservice that handles this responsibility. Obviously, the architects felt that this was a sufficiently complex component to warrant its own microservice. And of course, this isn't the only way that you could break this domain down into microservices. But on the whole, I think some good choices have been made here. And in fact, this might be a good time for you to pause this video and take some time to think about the project that you're working on. How would you break it up into microservices? What responsibility would you give to each one? And what data would each of those microservices own? In this module, we've looked at some of the key considerations involved in architecting a microservices application. You can evolve an existing system towards microservices by augmenting it with new microservices or by extracting existing functionality into microservices. We saw that microservices should own their own data, and they may consist of more than one process. Microservices need to be independently deployable. This requires taking care not to make breaking changes to the API or doing anything else that forces the clients of a microservice to be upgraded simultaneously with the service. The concept of bounded contexts from domain-driven design should be applied to identify suitable boundaries for a microservice. And getting those boundaries right is a critical factor in being successful with microservices. In the next module, we'll start to look at the practicalities of building microservices and what day-to-day development on a microservices project might look like.